Hi, everyone. I think we've been pushed back a few minutes, but I think we'll get going here. So if you want to come take a seat, you're welcome to do so. Welcome to the building electrification session as part of the long-term load forecasting workshop. My name is Jeff Deason. I am an energy policy researcher at Berkeley Lab. I'm your moderator for today's session. We will have three fine presenters coming up in just a moment. And before we do so, I will introduce them as they come up. I'm just going to take a couple of minutes to just provide some motivation for what's coming, which is going to be a lot of great detailed content on load forecasting for building electrification. And at Berkeley Lab, we don't do a lot of load forecasting per se, but we do a fair bit of generating scenarios and running simulations for what might be. And one of the points, and so I'm presenting, I want to show this figure, and really it's the left-hand side figure, and I'll talk you through it because it's hard to see. One of the things that comes up for us when we do this kind of activity is that you really get this very wide range of potential impacts of building electrification on electricity load, depending on what assumptions you make going in. And that variation is due to a lot of things, but two that I want to highlight are the pace of technology adoption, how fast will this happen, and also the efficiency of the adoption. How efficient are the electrification technologies you adopt? How efficient are adjacent measures like building envelopes and such that have a big role to play in controlling particularly peak electricity demand. So this left-hand figure shows a few different scenarios for building electrification and their impacts on site electricity use. I know you'll just see the shape of the curves, but the black curve is the AEO reference case, which we did not touch in this particular modeling effort. And then the other curves are, various assumptions of a combined efficiency and electrification pace. And again, you see this really wide variation. The purple line is basically a high electrification but low efficiency scenario. And here's where you see national total electricity demand really explode in that scenario. But then you see these other two scenarios. The green is more of a mid-efficiency, mid-electrification scenario, and the blue is actually a high efficiency but high electrification scenario. And in both of those cases, we actually see demand staying slightly beneath the AEO reference case. So there's a really wide range of potential impacts that we could see here. We see the same thing on peak. This is a different study that's already been published where we're showing the winter peak impacts from electrification in the residential and commercial sectors. And we can see here the sort of solid green is an efficient electrification scenario, and then the hashed lines are an inefficient electrification scenario. And again, you see something like basically the peak demand is twice as high under the inefficient electrification scenario as under the efficient electrification scenario. So efficiency can make a big difference here. The final point I want to make for motivation is we've been having a series of conversations with utility commissions on sort of identifying some of their most pressing electrification-related concerns. And this set of conversations was not specific to load forecasting, but a lot of load forecasting issues came up during these conversations. This is specific to utility commissions, of course, but there's a need to understand, for those commissions to understand when their systems might become winter peaking. They are interested in help with designing electrification scenarios, stress scenarios, and the like, understanding daily load shapes, understanding how efficiency can mitigate increases in peak, which is what the last slide spoke to, and also definitely with quantifying uncertainty with all of this. And so this is all by way of motivation for what our panelists are about to speak to. They are about to address all these issues to some extent, and there's definitely a lot of demand for work that will help figure out what's going to happen here. So with that, our first panelist is Ryan Jones from Evolved Energy Research, and I will switch the slides here.
Great. Thank you, Jeff. And Thanks for the invitation to come here and talk today. Pleasure to be with you. So I'm going to kind of give some perspectives on building electrification, largely breaking into, let's see, maybe we need to.
Oh, we're on the.
That work? Great. So a couple topics here that I'm going to try to cover today. First, I'm going to talk about high electrification scenarios, and I want to speak to kind of the uncertainty and both the uncertainty and the possibilities around the scenario generation side. I'm going to talk a little bit about how at Evolved Energy Research we build some of these bottom-up load shape future profiles for looking at both building electrification, but also electrification across industry and transportation. And then I'll dive a bit more in detail on just the heating side and talk about those impacts and give some perspectives there. So first, on the high electrification side, I think an important kind of contrast here is with these two approaches, one being forecasting and the other called backcasting, right? And oftentimes in the work that I'm doing, because at Evolved we do a lot of long-term studies looking at how to achieve deep carbon emission reductions, we're actually using more of a backcasting approach where we say there's some future net zero target for a state or for a country in 2050 and 2060. And to be consistent with that target, the following things are helpful in terms of bringing down the cost of that transition, right? And one of those being high electrification, which I'll get into a bit more. And then we'll say, what needs to happen in terms of technology adoption between now and then in order to achieve that end state in terms of a kind of composition of stock in 2050. That backcasting approach, if you look at it in the near term, you oftentimes see, potentially uptake of technology, which, on the face of it, to all of us, might outpace what we think customers are actually going to adopt based on the incentives and the policy, in play today and the cost of the technology, right? And that kind of points to this gap in between, if we're serious about these climate targets, here's what needs to happen versus what may actually happen in the near term based on kind of customer economics. The flip side of that is the forecasting approach, where it focuses really mainly on customer economics, and it oftentimes says, with existing policy, what type of adoption are we kind of likely to see? And as I'll kind of go through, these will oftentimes produce very different outcomes. So this is final energy demand for the U.S. economy, with electricity being just the piece there, the dark blue piece at the top. And in the annual energy outlook, we have, now for the decades that AEO has done this, very little, incremental both efficiency and electrification. If we look at this kind of breakdown of final energy demand between non-hydrocarbons, electricity being one of those, and then hydrocarbon demand, we get this picture here, right, which is kind of part of the fundamental challenge of decarbonization. And what you realize if you kind of crunch the numbers on what we're going to do on this hydrocarbon demand side without just reducing service demand, you realize between efficiency, drop-in replacement fuels, whether it's biofuels or e-fuels, the scale of the challenge is beyond what those types of solutions may be able to provide. And thus, pretty much all kind of net zero scenarios that we model that are relatively low cost have some degree of electrification. Now, sometimes we run scenarios, and this is from the Princeton Net Zero America work, where the scenarios may be kind of delayed electrification. But it's you know, I think less plausible in these future scenarios to think that we will end at a state of just low electrification and that is going to persist given the relative economics of clean fuels versus the electric technology alternatives. So that's kind of the reality on the electrification side, which I think many in the room, you know, I'm kind of preaching to the choir here. So just from this kind of first section, a couple of general conclusions. You know, the forecasting and backcasting approaches are producing very different long-term forecasts. You know, AEO and many, you know, not my colleagues who are going to speak here next, but many utilities are still looking at, you know, forecasted load with little or no load growth. And, you know, kind of the type of load growth we've seen in the past several decades where it might be, you know, 0.2% per year. In these high electrification scenarios, and the electrification future study was one of the first to kind of really highlight that load growth potential, where, you know, 2 or 3% annual growth is very possible if these, you know, if these levels of technology adoption that a backcasting approach would imply are achieved. And, you know, that's far more in line with kind of load growth that we saw from the last century rather than this. And the last point here is, I think the time that we're in right now, where, you know, we've just passed, you know, IRA at a federal level, we have a lot of states with, you know, aggressive climate targets, but we're still at a relatively early point on any of these S curves of adoption. You know, I think in retrospect, we may look back at this period and see kind of like peak deviation, right, between these two approaches, right, where we have very, you know, very different potential perspectives on how quickly electrification may unfold. And I mentioned IRA, you know, I think our perspective is that this is likely to accelerate kind of electrification trends by 5 to 10 years. But the forecasts of these impacts differ widely. And for those who have seen the new annual energy outlook for 2023 that just came out, you know, a month or two ago, you know, at least from the annual energy outlook, you know, their projections of the impacts of IRA are quite anemic compared to some of the others, including ours. So I'm going to change gears and talk a bit about projecting load kind of bottom up. The way that we do this is with a kind of stock turnover accounting model. We call this model energy pathways, but basically it breaks the, you know, economy down into subsectors. It projects service demand through 2050. We do a stock turnover with user input assumptions on what sales may be, and sometimes those sales rates are informed by other adoption models. Sometimes they are themselves basically the outcome of a backcasting approach. And then we get, you know, final energy demand that we then multiply by essentially unitized shapes on a subsector basis, right? In this example, we've got a lighting shape, and this is kind of a month-hour average of this lighting shape. If we do this for all the subsectors, we sum them up, we basically get a bottom-up estimate of load in a future year. These unitized shapes are oftentimes tied to a historical weather year. So in just a moment, I'll show kind of a couple example outcomes of this, but the historical weather year is an important kind of dimension that we look at. And I know there's going to be some discussion in one of the sessions about integrating future climate change into these types of forecasts, which is one thing we're working on. In the interest of time here, I'm not going to get into the detail of how we do some of the additional kind of statistical reconciliation, because this is always a big problem when you do, you know, bottom up and top down comparisons, as Elaine from NREL will tell you. I worked with Elaine in the electrification future study, and I know that was something that a lot of us have struggled with for a long time. But I think we've made at least some kind of progress on that score. And as we continue to improve the underlying kind of unitized shapes for each of these subsectors, the hope is that that kind of reconciliation step becomes less vital as a correction, and kind of the importance of that particular step goes down. So I mentioned the sectoral granularity. This is a breakdown of basically final energy demand categories in the annual energy outlook, and these are things that we use. They also are kind of the categories that are used in the building residential and commercial building surveys that DOE does in the MEC survey for industry as well. So this is kind of a sample load shape of what this looks like for high electrification, showing 3 years here, kind of three, say, economic years, right? So there's 2021, and then moving down 2035, and then 2050. This is for New York, which Arthur is going to talk more about. And then across the x-axis there, we have different weather years. So this is basically asking the question, in the year 2050, if we had high electrification and the weather matched, the weather that we had in 2011, what might the load look like in the state of New York? So you'll kind of notice quite a bit of peak variability year to year, and it's one of the I think an emerging area of research, which is, as we do kind of more planning for these high electrification scenarios, making sure that the models that we have and that are using are taking into account multiple weather years due to kind of differences in winter peak impact. This gives you a snapshot of just looking at these peak loads, and now this is for the lower 48 states. The size of each of the kind of pie charts are based on 1 and 2 peak load, and then the seasonal split between fall, summer, fall, spring, summer, and winter are based on kind of the count of the top 100 load hours across multiple weather years. So today, we're largely, as everybody knows, a summer peaking system. There are parts of the U.S. today that have higher electrification of heating already. So in the Northwest, we see winter peaks. We also see winter peaks across parts of the Southeast, where either electric furnaces or electric baseboard heating, it's in Florida, for example, the absolute peak load, if you look across multiple weather years, typically occurs in the winter. Because of that heating load in winter mornings, right? Interestingly, if you look at Florida moving across from 2021, 2035, 2050, Florida is actually one of the places that becomes more summer peaking, because if you take the electric baseboard heaters and you move those to heat pumps, you can actually reduce your winter peak more than any incremental electrification is going to grow that winter peak, right? But for the rest of the country, you'll see by 2035, there are a lot of places that today are largely summer peaking, which become dual peaking. And by 2050, anywhere kind of north of Maryland, right, has a pretty strong winter peaking signal in these types of high electrification profiles. So I'm going to focus now in a bit deeper on just the heating electrification side. So as Jeff laid out at the beginning, the projecting these electrification impacts are quite difficult for buildings, with many factors kind of compounding together to create these nonlinear effects, where small changes in assumptions can result in very large differences in the projection for peak load and the implications that has for, system planning, distribution system capacity, all sorts of things that we care about. So I've talked a bit about the rates of electrification in the forecasting and backcasting approach, but the other bullet points here all relate to kind of different aspects of either the building, the heat pump, technology itself, or some of the climatic conditions, whether it's, spatial diversity factors or future climate change, that kind of all need to be taken together to project these types of future impacts. Just to highlight one, for heat pumps, the assumption around heat pump sizing is critically important for understanding peak load impacts. So, as the temperature drops, not only does the coefficient of performance on heat pumps go down, but the BTUs of sensible heat also drops, and that's in contrast to, say, a natural gas furnace, where it's, if you're producing 70,000 BTUs out of a natural gas furnace, doesn't matter if the temperature is 0 degrees or 50 degrees, you're still going to have the same capacity, and that's different with a heat pump. Now, one of the things you can do with a heat pump is you can actually oversize them, right? And that helps with kind of peak load impacts, because it sometimes means that you don't have to switch over to electric resistance when you otherwise might, in order to maintain a set point in the home. But a larger heat pump is more expensive. And, today, if you look at most of the heat pumps coming in, because they are, large, a lot of heat pumps today are largely targeted at air conditioning, and then you get supplemental heating. They're sized for air conditioning load in the Northeast, right? Which, if you size it for air conditioning load, it's going to be undersized for your heating load in New York. So, that's just kind of one example. And based on that heat pump sizing, you can, the implication for peak load can be quite dramatically different. So all of these kind of, detailed inputs that you need to project building heating, my kind of proposition here is that a lot of this can be summarized or synthesized into kind of metrics, just looking at the load factor for heating equipment, and that doing so can actually be very helpful for kind of inter-model or inter-utility comparisons, when oftentimes you'll get, you'll see two studies and they come up with very different, peak load impacts. And we've been involved in some of those in places like Massachusetts. And you wonder, you projected, 30 gigawatt peak and somebody else projected a 50 gigawatt peak, what's the difference there? And kind of synthesizing these together to look at utility factor can be really helpful. So based on the experience that we've had modeling this around the country, I want to lay out a couple different ranges here. So, for a utility factor, which is, basically the average consumption divided by the peak for heating equipment in a building, 3 to 10% is from what we've seen is very possible in warm climates, but in cold climates, this kind of represents a worst case scenario. And so if you have 3 to 10% and you're in New England, you're going to have an extreme winter peak load. And sometimes it can mean that the underlying, assumptions need to be revisited, or it also can mean there could be opportunities, whether through policy or other things, to kind of help shape the direction of future heat pump adoption. The 10 to 15% range, I would call this our current best guess for utility factors in populations of heat pumps in temperate climates. So this is kind of at a state level. And then a 16% utility factor plus, I would say probably has a strong possibility of underestimating peak load from what we've seen. And these are two examples. So again, to go back to the New York example, this is the same weather years that I showed before, this is just looking at building both residential and commercial heating loads. And we see a load factor of 14% there. So those two lines, one showing the peak and the other showing the average. Whereas here in Florida, we have a 3% load factor, right? So, you know, you can get a meandering Gulf Stream and a really cold winter morning in Florida, which creates a high peak, but the average heating load in Florida is quite low. But, you know, of course, if you had a 3% load factor and you applied that to the annual heating demand in the Northeast, right, you're going to get a super peak load. And then finally here, I want to highlight, you know, the fact that the opportunities for, you know, I think flexible load and all this, they are, I think, intellectually understood, but I think the magnitude of the load in these winter peak periods that have some type of built-in storage, whether that's thermal or chemical in the case of electric vehicles, is really significant. So this is the 2011 peak again from that kind of New York strip, and I've broken that down by a couple subsector categories. So the red on the top is the space heating. The lighter blue next down is water heating, and then we have light duty vehicles and other transport. So those colored shapes, if you look at their contribution to peak, that's basically 53 gigawatts, whereas other loads are contributing 16 gigawatts to that peak hour, right? And this is not to say that we can shift all that load away, right? But it gives you some sense of you may not need a really heavy touch on those types of loads to actually make a pretty big difference in terms of a system operator's peak in that time period. So happy to answer any questions during our discussion, and yeah, appreciate the intention. Thank you.
Literally to the second on time. That was impressive. All right. And next up, we have John Black from NYISO New England. And I will pull this up.
Okay, good morning, everyone. Here to talk to you about our building electrification work in New England. Start with a little intro and background, go through our methodology for the various components of our methodology, and share some results and then some closing thoughts. I'm going to skip the material that's information about NYISO New England, because you'll be able to review that on your own time after the conference. So when I say building electrification, I really mean heating electrification forecasts. Our electrification work in the building space really is focusing on space and water heating. What I will show you today really is walking through the space heating portion of our heating electrification forecast, because there's a slide towards the end that will show that our water heating results aren't that compelling in terms of their magnitude of impact. So I think if you understand the space heating, you understand our heating electrification forecast. But essentially, you know, our New England states have really lofty or aggressive goals about decarbonization, economy-wide decarbonization by mid-century. and some states have most states have legislated mandates, and I think one state, actually I'll talk about this in the next slide, so I'll save that. And I already said space heating. We're focusing on space heating in this presentation. But so here are the list of all the CO2 emission reductions goals and mandates in New England. So of the 6 New England states, all of them except New Hampshire have, really active mandates and goals. And, the reductions are normally tied to something around 1990. But anyway, you see 80%, 90%, 100% carbon neutral, so on and so forth. And obviously, the heating sector utilizes a lot of fossil fuels. So this is sort of the background of why we're doing what we're doing. Okay, so moving on to methodology. We've been forecasting electrification for 4 years now. This past forecast cycle, we really were eager to completely overhaul and expand our methodology. We started off focusing on just air source heat pump adoption in the residential sector, partial and full heating applications. So basically had 2 heating pathways in residential only and nothing in commercial, and no consideration of water heating. And so we felt like our methodology was rather incomplete, but it was a good starting place. So we worked with a consultant in advance of our forecast cycle this past year. And we really were interested in trying to leverage, publicly available data to kind of align our work with what we think other folks would be doing in the industry in a similar vein. So what that meant ultimately was that at the root of our methodology is a lot of data in NREL's ResStock and Comstock data sets. And the work that we did and our methodology really was broken down into 4 steps. I mentioned this yesterday morning, but I'll reiterate them for folks that weren't here. We first, this is all information that we didn't really have, and certainly, or certainly didn't use in our forecast prior to this forecast cycle. So this was a huge opportunity for us to learn more about what we're doing and advance what we were doing as well. So we began with the, comprehensive building stock characterization, what the various sizes and numbers of buildings were, how they're currently heated, what the, delivery mechanisms are, ducted versus not ducted, everything that would, be needed for, doing adoption and modeling subsequently. Next was developing a set of heating pathways. And what that means is essentially, think air source heat pump in a, detached single family home. That would be a heating pathway. And then along each of those heating pathways, basically do some modeling and develop some adoption forecasts for each one of those heating pathways. And then lastly, for each, unique combination of heat pump technology and building type, what is sort of the hour by hour relationship between ambient air temperature and demand, electrical demand. So on the right, you see sort of a flow chart, and thanks to Victoria Rojo in the audience here, she managed to distill our entire new methodology into one slide, which I am grateful for because I would have made a total mess of this. So what we ended up with on the residential side were 5 different residential building types, and on the commercial side, 14 different building types, and 7 space heating pathways and 1 water heating pathway on the residential side, 10 space heating pathways and 2 water heating pathways on the commercial side. And then, there's sort of some flow and math about all the different combinations when you get to the modeling step of how many models you're going to need. Short story is a lot of different models. So certainly a lot more complexity at the end of the day with our new methodology. And this was, a lot of what we were interested in pursuing, so that we had more granularity, more fidelity in our modeling and understanding. Obviously, we're forecasting kind of in advance in a lot of ways of what these emerging trends will end up looking like. So we wanted to make sure we had our, hooks and levers in our methodology so that we can recalibrate as necessary as the future emerges. So in the building characterization, these are a couple of just basic heat maps on the residential side on the left and commercial on the right of what's the legacy heating fuel sources. And all told, in residential space, you're looking at a little bit north of 80% of all households are using fossil fuels to heat their homes currently. And in the commercial side, north of 70% on a square foot basis of commercial buildings are using fossil fuels to heat their homes. And you can see, the various ranges of, fuel oil versus natural gas versus propane. And a lot of this is, a direct result of where gas pipeline availability is and things of that nature. So if you tend to be more rural and in the northern climes of New England, there's a lot of areas that tend to be more delivered fuels, think of like heating oil and propane. So definitely wanted to capture all that in our work and understanding of the space. In terms of pathways, on the residential side, here are the variety of different heat pumps that were incorporated into the methodology. You see ducted and ductless air source heat pumps, both full heating, meaning they're providing all of the heating for the building in question, and partial would be, there's some, unspecified backup heating source, non-electric source of heat. And I'll talk about the specifics of in the modeling of what the differences are. Ground source heat pumps, air to water heat pumps, package terminal heat pumps. And then on the commercial side, there's a little bit more diversity. One noteworthy difference is these rooftop units on the commercial side of things. And then there's a lot of overlap, and then there's variable refrigerant flows or VRF systems. But, a few more pathways on the commercial side than in the residential side. And I think that's largely attributed to, in the commercial space, you have a much greater range of building sizes and types. And so you're going to need, a much greater range in different types of technology, heat pump technologies to provide that heat for the building. In terms of adoption modeling, I have a bunch of words in the slide. And I imagine there's going to be a lot of interest because this is one of the greatest sources of uncertainty. How do you model this stuff and glean what the future might look like in terms of the pace and the mix of heat pump adoption out 20, 30 years in the future? It sounds like a crazy endeavor, right? One of the things that we were really drawn to the consultant that we selected for the work that we did to advance our methodology is they actually were really thoughtful and had innovative ideas about how to do the adoption modeling, leveraging sort of Bass diffusion modeling. But, they waded into the abyss, I would say, in sort of trying to come up with a methodology that captures at least the rudiments of what would inform adoption. So I know that there may be some questions that will invite me into that abyss to answer some very highly granular, detailed inputs into this modeling. And, I'm okay with that. But, I think big picture, I think that what they did was compelling. It yielded reasonable results. And as a forecaster, that's what we were seeking. And really, I think the methodology they built it holds a lot of potential value in the future because what they did was they did probabilistic modeling based on Monte Carlo simulations of a few of these features that I'm listing here so that they could develop sort of clouds of possibilities with relative percentile rankings of adoption rates and paces and stuff like that. And so I don't think that I think it needs more maturing as a methodology, but we really were drawn to that because, we're really interested in developing the capabilities, hopefully in-house, of developing probabilistic scenarios for each of our exogenous forecast, heating and others as well. So all that aside, the adoption modeling looks at all these potential pathways that it has outlined and looks at the details of the existing building stock. And then state by state, looking at sort of the relative state of policy support and policy drivers that are pushing and promoting and underpinning the adoption in each state, as well as some, current state of economic considerations. So these would all include building type and sector, existing heating fuels, existing heating and cooling delivery systems, and payback period level of policy support. We do have a range in New England of policy support and the relative incentives. I do think the IRA was just hot off the press when we were doing this work. And so there is some consideration of the IRA, although if you hold me to the flame, I won't be able to tell you specifically what that might be. But the pathway adoption modeling is performed at the state level for each of the sectors. In terms of the BAS diffusion modeling, ROI, policy support, technical barriers, and the current levels of technology saturation, that's something that we don't have actually a complete picture of. So there's a lot of gaps in our understanding in terms of the inputs to what this BAS diffusion modeling would look like. In terms of the demand modeling, this is something we were very interested in. Basically, we want to develop first the hourly heating load relationships as a first step to ambient temperature for all the building types, and leveraging the heated usage profiles in NREL's ResStock, Comstock databases. So for each pathway, they basically selected a reference heat pump. I have slides at the end that I'm not going to cover, but it lists all of the pathways, the reference heat pump system, and plots a comparison of all the COP curves across the temperature scales, because I think that's really where the rubber meets the road. But I won't cover that as too much detail, but it's in the back of the slide deck for folks if you're interested. But basically, based on that heat pump COP sort of curve, you're converting that heat usage profile into hourly electrical demand. And then as a third step, the difference between full heating and partial heating, number one, all heating was initiated when temperatures dip below 62 degrees Fahrenheit. But this is very key for partial heating. When the temperatures dip below 20 degrees Fahrenheit, we assume no electrical demand. And you'll see when I get to the adoption results that there's a significant share of our adoption forecast that is in this partial heating category. So, think about that in terms of this uncertainty. And then, some details for full heating. There's electric resistance backup that's used to meet any of the demand that's not met by the heat pump, basically when temperatures are below the minimum operating temperature of the heat pump. And basically we ended up with these hourly models for all combinations of building types and heating pathways. In terms of results, in the residential space heating section of this heating world, you see in the upper right, this is sort of the annual adoption with layers by state. Sort of the peak adoption happens in the late 2030s. And sort of as a rough check, that peak rate of adoption is equivalent to about 3.5% of households electrified in that peak year. And this is an important check because, assumed here in the details was a 20-year measure life for HVAC equipment. So this, is about, 60-70% of that total stock turnover in any individual year in our modeling. Overall, about 4.4 million residences electrified by 2050, and that dashed line is the end of our 10-year forecast horizon. So we have this modeling going all the way out to 2050, but our CELT forecast only goes out to 10 years. All told, fuel-based heating, about 84% of it is electrified to some degree by 2050, which is almost 70% of the total housing stock. And that's split roughly half and half, partial, full heating. In commercial space heating, story is bit similar, although there's maybe there's a greater preponderance of full heating applications that I think is attributed to that rooftop unit technology, as well as, you know, the assumption that in the commercial space, adoption is more of a, you know, the business case has been made. It's a business decision. And so, you know, there's maybe more likelihood that they're going to replace their whole heating system. But anyway, in the commercial space, our adoption forecast peaks by mid 2030s. Overall, about a little south of 80% of the fossil fuel based square footage in the commercial space is electrified by 2050. And the split, 30% partial, 70% full heating. In terms of hourly demand, this is where things get really interesting. So this is just a very small piece of our forecast looking out at 2050. So this is residential space heating for single family detached homes. And the left-hand plot shows the hourly demand profile for each pathway on a particular day. This was a, you know, rather cold day in Vermont. So you see the various traces of hourly demand in the solid lines, and then the dashed lines with the blue circles. Right here, you see the temperature profile. So, you know, this day, all of hourly temps in Vermont were below 20 degrees. So that means none of the partial heating pathways were being utilized at all. Zero demand from all the partial heating applications. But then you take those traces, you fold in January 2050 heat pump adoption for each one of these pathways, and you end up with the plot on the right, which is the total hourly demand profile on this particular day for Vermont, with, you know, morning peak of about 600 megawatts, which is not too far different from what Vermont's current annual peak is today, just put it into context. And you can see the various slices by heating pathway, with central full being the purple and ductless heat pump full being the sort of orangish colors. What does it mean in terms of our seasonal peak forecasts? This plot is inclusive of all electrification, but just to give you a sense, this is basically the peak eliciting portion of our probabilistic forecast for summer and winter out over our 10-year forecast horizon, with the red shaded areas being our summer peak demand and blue shaded areas being our winter peak. What we refer to as our 50-50 demand are the dashed in the middle of these sort of percentiles in our peak eliciting portion of our forecast, and our 90-10 is the top dash trace of each one of these. But really the takeaway is not only is there dramatic convergence because of the pace of electrification that we're forecasting, but by the end of our 10-year forecast horizon, the 90-10, actually not even 20, by 2031, if we get a really extreme cold Arctic blast in New England, according to our forecast in 2031, but maybe have a mild summer without a, you know, significant heat wave, we might have a winter peaking system by 2031. That's basically what this says to me. Okay, so in 2050, what does this mean? January 2050, this is what all these projections sum up to. And this is by sector. So you're seeing here a peak in the morning total of about 25 gigawatts. This is kind of what we refer to as that 50-50 forecast again. So this isn't the most extreme weather in the winter. This is sort of our typical peak return period of 2 years. So you see the residential space heating in green, commercial space heating in blue, and the top two slices is what I was talking about. That's residential and commercial water heating, and those slices are rather small, so they're not really worthy, according to our results, of talking too much about in the whole scheme of things here. So one interesting feature of this plot is that it's now we're shifting not only probably to a evening peak or a winter peak, but also a morning peaking system. So that's something that we were really interested in. I don't know how important of a load characteristic that is, but it's certainly a major takeaway that we've sent, shot across the bow to all of our end users, being like, hey, start thinking about this, not sure if it's important, sort of thing. But anyway, I guarantee with 100% certainty, this is what heating load will look like in January 2050. Some closing thoughts. Really, it's kind of a strange business that we're in. We have a need to forecast out decades in advance. What are the energy and demand implications of technologies that have yet to emerge, the pace of trends that are yet to emerge? Because basically our forecast informs what that shape of the grid of the future might look like, right? Investments and, the direction of planning and things like that. So really, we're just trying to paint a picture. We're starting off a lot of uncertainty. So however blurry that picture is, doesn't matter. We're going to refine it as we revisit this process every year as more data and the trends start to emerge. In terms of sources of uncertainty, I'm running out of time. These are basically a lot of different words to say a lot of the same things that Ryan said in the prior thing. Certainly the rates of adoption are a huge source of uncertainty. What that equipment mix looks like, heat pump sizing, what the backup heating looks like. It was resistance based, how common is it going to be? How much will full electrification take off, full heating electrification? I think one of the things that's really interesting is, the behavioral shifts, right? I think what Ryan said is, you just can't deliver as many BTUs when it's really cold from a heat pump, right? The volumetric flow in the air of BTUs from a heat pump is different. It's less when it gets cold. So some of those demand profiles that we're using based on Comstock and Resstock are based on fossil fuel heating. So that to me is a big question mark. We might see a less peaky load shape as an implication because of this sort of technology constraint where, there's these heat pumps may be delivering BTUs more around the clock. Anyway, so that's it. I'll stop there. Thank you.
All right, thanks, John. And last but not least is Arthur from ISO New York.
Good morning, everyone. Really pleased to be here. It's a great conference, and I'm glad that ESIG is looking at probabilistic forecasting and long-term forecasting in addition to some of the things that are involved with real-time. So very pleased to be here. I've done forecasting for a very long career, both at an electric utility, investor-owned utility, as a consultant, and for the past 20 years at the New York ISO. I've split my time between real-time and long-term, so I'm very happy to speak today on this topic. The New York ISO is the grid operator for the entire state of New York. We're an independent entity. We're not a governmental agency. We operate the power grid, which means we schedule generation, dispatch it, and monitor conditions 24/7. We also operate the power markets, where independent generators and buyers and sellers of power interact, and they make the market. Their prices, bid, and generation dispatches. That's all controlled a lot by market transactions. And we also plan the system, which is where I have spent my career. And the idea about planning the system is you always want to keep the lights on. As an operator, you always want to keep the lights on. From a marketing perspective, the transactions must be feasible to keep the lights on. So keeping the lights on is one way or another our primary business. And that means that when we do a forecast, the supply needs to meet or exceed that, including some reserves. So that's kind of the framework. Our focus is always on getting that forecast right so that planners, the other planners, the demand side or the generation planners and all that, they can, if you give them a good forecast, then they'll make sure, their job is to make sure that the supply is there. For today's presentation, I'm going to start it. I cover 3 topics. I cover the technology of a heat pump itself, very high level for like a single site. And you'll see illustrated some of the theory that goes into why we're concerned about heat pumps and grid reliability. Their performance decreases as it gets colder. And so you have to either increase capacity or you have to provide some additional heat. So, and then the third part, well, I'll also talk about res stock and how we use that once we have a sense of the performance of a single heat pump, the usage characteristics for the entire state, we leverage from the res stock database. And then finally, I'll talk about the forecast results. So cold climate heat pumps is where the focus is, not heat pumps that you might purchase for your summer and then you, whatever capacity is left, provide some heat. No, if we're going to meet the climate goals that are set by state agencies or the federal government, we've got to have cold climate heat pumps in New York. And so we've looked at their performance characteristics. They do provide lower temperature heat than a gas furnace. You do need to provide more air handling. And there's a DOE challenge to design even better heat pumps than are on the market right now. And so we're taking into account as we proceed, the forecast trends of efficiency of heat pumps are built into our market. So this single chart helps illustrate the problem. The diagonal line, starting at high at the left and then decreasing, it shows that as the temperature gets colder, your heating requirements, say for a single family home, are increasing up to about 70,000 BTUs per hour. And the heat pump performance, a 5-ton heat pump is going to provide maybe 50,000 BTUs per hour when it's fall temperature. And that gradually decreases due to essentially the law of thermodynamics. You can bend that a little bit, but unless you have a ground source heat pump, which is flat year round and flat with the temperatures, this is the performance one way or another for an air source heat pump. At a certain point, the heat pump output is less than what you need for the home. And so you need some supplemental heat, either from a gas furnace or electric resistance heating. Now, if you're going to electrify and you're not going to have gas furnace, then that orange triangle needs to be provided by some form of resistance heat. So this in itself, if you understand this, you understand why heat pump performance degrades at the coldest temperatures of winter in the Northeast, and why you've got to make some allowance for supplemental heat. Now, for a 5-ton system, you know, this is what you have. If you are going to match the capacity of today's gas furnaces, you would need 2 5-ton furnaces. So you can eliminate the orange supplemental heating for a heat pump if you go to a 10 or a 12-ton system. That theoretical performance, now you see what a building load model from DOE2 provides. Of course, all the partial load conditions. This represents about 4,800 hours in the summer, in the winter, And if we were going to dig into this, we'd see how much you get from the environment, how much from the compressor. There's some parasitic heat to defrost, just like your refrigerator, and then energy provided by supplemental heat. So again, the challenges of a heat pump: reduced heating, degradation of efficiency with temperature, and a high discharge temperature. What that means is the compressor has to compress air from, say, ambient conditions of -5 all the way up to about 100 to 120 degrees. Room air conditioner in summer only has to compress from 70 degrees up to 100. So all of these mean you either have to provide supplemental heat, or you have to increase the capacity of your heat pump. So this is the challenge. This is 4,200 hours. And this chart is, you can derive from this chart what the load factor is, the utility factor that Ryan mentioned. The year 2018 weather-wise was a great year. It brought us to the 1% design weather conditions that ASHRAE specifies. So it was a great weather year for us. And the output of the heat pump kind of maxes out at about 7 kilowatts. And there's about 400 hours remaining where you need supplemental heat. Now, those 400 hours are not concentrated only in a couple days of the year. This chart, and it's derived from the hourly output of the DOE model, which is the same basis as the res stock. They essentially use the same approach. You can see that the heat pump is clipped or capped, or its maximum output is about 6 kilowatts thermal to heat the home. But this particular home, 2,000 square foot home, actually got up to between 16 and 18 kilowatts. And this orange shows you hour by hour during the first 5 months of the year, hey, you need more than just a few hours in just a few days. So it is an operational challenge. If you're in the Northeast in a single family home and you only have a 5-ton heat pump, you are going to need either some gas backup or propane or electric resistance heating. Now, when we analyzed the res stock data, we first did it by type, which of the utilities in the state of New York, and by building type, single family, multifamily. We found that was not the way to slice the problem. We, in fact, decided after review, it was much better to look at size of footage, because the maximum size of cold climate air source heat pumps manufactured today is only 5 tons. Now you can get much larger size for rooftop units used in the commercial sector, but what's available in the residential sector is basically 5 tons. And this red line shows, of all the roughly 7 million homes in New York, how many of them fall above and how many of them fall below the 5-ton capacity. Now, the one comment is there are 8,000 and 11,000 square foot homes. These are residential, multifamily, very large apartments. New York City has the most dense multifamily sector anywhere in the country. And so there's a lot of homes that are represented in large buildings. So what this means is, if you're only going to put in a 5-ton system, there's a lot of capacity that needs to be provided with some form of resistance heating or dual fuel gas. So that information is basically how we got the performance characteristics of air source heat pumps and got the peak demand versus the energy right, the load factor, and of course, trying to understand the seasonal characteristics. But for a single family home, that's not what you want to build a forecast on. We went to the ResStock database. They modeled 33,000 homes with the same Do2 software. And they actually, I think, did 500 to 600,000 across the whole US. So you can, if you're in a different part of the country, you can replicate this work for your own service territories or for your own studies using the ResStock data. It is a representative of the 2018 housing stock across the US. So in New York, I have the different major investor-owned operating companies and the New York control area as a whole in total. And I've stratified this by the building size categories that are embedded within ResStock. And this is telling us the number of homes by size of square foot. There's just under 7 million homes. From ResStock, the same data source, the bottom right corner, it says 80,717. That's the average residential gas heating consumption, 80,000 BTUs. The ResStock data agrees with 2018 EIA. This was our control tool, making sure that we accounted for all the space heating needs. The bottom side, the bottom chart is telling us by size of home and across the operating utilities, what is the capacity in BTUs per hour? So your furnace size in a single family home in the upstate area, you're going to need a 70,000 BTU per hour furnace. For those of you who heat your homes with gas, it's probably 70,000, 80,000, 90,000, some higher. And these are the averages. This is not the distribution. So this is the mean size, not the high end. Some homes are going to have even higher furnaces. We can convert this annual energy and winter capacity in the next slide, the equivalent annual energy of a heat pump by size of home across the different geography of the state, that 80 million BTUs per year, 7,570 kilowatt hours a year. And you're going to need a kilowatt peak demand capacity of about 6.5 to 7 kilowatts on average. That's what the compressor load would be. And that should be the equivalent. If you had the average usage, this is what you would, your heat pump would do this. When we did our technology forecasts, we modeled as follows. We had full source, air source heat pumps, full capacity. So if the home needed, if it needed 15 tons, if it needed 10 tons, whatever, 27% of the homes had full capacity air source heat pump, no supplemental heat required. 20% of the homes would require some dual fuel because the heat pump was not sized for the full load. 8% of the homes just installed all baseboard electric or electric furnaces, so they did not go the heat pump route. 5% of the homes had ground source heat pumps, and then half of the homes with dual fuel had supplemental resistance heating. The other half of them would use gas. The climate goals in New York do not require 100% conversion to electrification. So this is the technology basis, 70% overall, 60% of the homes because the supplemental is installed in some of the other homes. We have the load factors, some are 20%, some are 17%. Kilowatts and kilowatt hours per for a 1,600 square foot home. Ryan mentioned a 14% load factor. We've got 17% for some of our homes, 20% for others. So this was our technology pathway. And this is our saturation curve to use Ryan's terminology. We started with where we needed to be in 2050 and worked our way back with an S curve. Now the S curve is we can control with a few parameters. It's a 2-parameter function. It's a sigmoid function. And we start with, we know that there's some existing heat, electric heat and heat pumps already in 2018. And this is showing in at various decades what the penetration is going to be. Now we can adapt this curve very easily, 2 parameters. If you give the endpoint and the start point, you can make the curve the adoption either faster or slower. This is the type of performance that we've seen, the type of adoption rate we've seen for solar PV. At a certain point, it ramps up quickly, then it becomes linear, and then you gradually decrease. Now we could adopt this for different rates of change, but this is what we've chosen for all the technologies. We got some guidance from the state utilities as well. What are their adoption rates? We had 3 scenarios. We developed a baseline with 40% fossil usage and 60% of the homes some form of electric heating technology. And then we had 2 policy cases where only 10% of the homes are heated by some form of fossil. And the difference between them is either more or less adoption of resistance heating and supplemental heating, and more or less adoption of air source heat pumps. And so both of the policy cases would meet a high level of clean energy, but you're going to get different peak demand impacts. So I'll have go through, I won't have a lot of time to go through the summary of the forecast. We do a 30-year horizon. We develop annual energy, seasonal peaks, and we also have 2 bandwidths, a 90th and a 99th, and we do hourly load. So this is going to be for all of the forecast categories. We use end-use models for the base load that exists right now, and then we have separate forecasts, bottom-up, for all these other categories. This is our peak demand, summer and winter out from current, our actuals and our weather normalized peaks. And we move in New York from winter to summer, from summer to winter, in about the mid-30s. We've seen this crossover fairly consistently over the past few years. And we reach in this current version of our forecast about 50,000 megawatts statewide, as compared to about 30,000 megawatts right now in the summer. If you look at the components of growth for all those categories, the components of growth are primarily in green, building electrification, and EV peak demand charging. And then so this is showing the components of in the summer, where we have a lot of negative additions for energy efficiency and other categories. But this is how we look at all the components of the forecast. This is a view of the hourly loads in 2035. It's very similar to of the base load characteristics that we are all familiar with in the Northeast these days. Summer peaking and winter peaking is a lot less. This is for one particular zone in our in the New York area. This is what the load profile from Restock is for a single year And this is on a per customer basis. The point I want to make here is we match the weather patterns for the base load to the weather patterns, same weather patterns driving the heat pump, so that when the cold weather affects the heat pump, it's correlated hour by hour with the temperatures that are driving the rest of the system. So that when we add these all up, we are adding apples and apples. We're adding coherently hour by hour throughout this entire 30-year process. And this is the final result. The two lines that should be of interest are the green line, which is the base load, similar to the patterns that we have today. The blue is the impact of all the electrification, all the large loads, all the energy efficiency. We have some robust storage that also clips peak demand, but we're basically in the mid 50s thousands of megawatts in winter, and clearly the blue line in winter is greater than in summer. There's not much electrification effect from building electrification in summer because the performance of a heat pump and the performance of central air conditioners are virtually the same. So I hope that I didn't overstay by too much. I think I'm pretty close on time. And do you want me to just stay up for a minute or two, or?
We can go back.
So thank you very much for listening to that. I hope it was not too rushed, but